Hello and welcome student in the fifth lecture of this mechanical properties of the fluid lecture. So student, first of all we will discuss the part that we have discussed in the previous lecture. So you will get it very easily, so you can keep in your mind for the long time, and it will be very easy for you if we are revising that one part. So first of all we will revise the part that we have learned in the previous lecture. So the first part that we have discussed in the previous lecture is this is the first derivation or the expression that we have learned, and this is the diagram of that expression. So in which we have just considered the container in which, or the vessel in which the water is poured, and we have imagined the imaginary cylinder which has been dipped inside that water, and as you can see the area of that cylinder is A. Now the area is cylinder and the h is the height. So after that we will divided it into the three type of forces which has been acted over that cylinder, which has been applied by the water which is lying over the top surface of that cylinder and below the bottom surface of that cylinder. So these three forces we will learn first. So students, as you can see, those three forces are as the first one is the force F1 bar. As you can see it in the diagram, it is at the top surface of that imaginary cylinder and it will be acted downward at the top surface of the cylinder. So it will be due to the weight of the water column which will be lying above the cylinder, which will be lying over that cylinder. So that will be the force F1 bar. Now in the same way, the force F2 bar you can see in the diagram at the bottom part of that imaginary cylinder. So force F2 bar acts upward at the bottom surface of the cylinder and is due to the water below the cylinder. So these are the two forces, that is F1 bar and F2 bar, that we have discussed. Now the third and last one, the force of gravitation. The gravitational force on the water enclosed in the cylinder is mg. So m is nothing but the mass of that water and the g is nothing but the gravity or the acceleration due to gravity. Now as the water is in static equilibrium, means the forces will be get balanced, so that is nothing but the static equilibrium. So the forces on the cylinder are balanced. So these are the three forces you have to keep in mind, student. The first one is F1 bar, which will be lying over that over the top surface of that imaginary cylinder due to the water which is lying over that imaginary cylinder. And the second one force is the force F2 bar, which will be below the surface of that imaginary cylinder, which will be acted the water which is lying below that surface of that imaginary cylinder, and it will be in upward direction as you can see in the diagram. And the last but not the least, it will be the gravitation force mg will be acting due to the water. So these are the three forces that we have considered for our expression. Therefore the balance of these forces in magnitude will be given as the F2 is equal to F1 plus mg. Now the next things that we have to consider is the P1 and the P2 are the pressures at the top and the bottom surface of the imaginary cylinder respectively. Means the P1 will be the pressure which will be acting over the top surface of that imaginary cylinder, while the P2 will be the pressure which will be acting over the bottom surface of that imaginary cylinder. Now we can write with the help of this equation, that we know the equation that pressure is equal to force upon area. By the rearranging we can say that the F1 is equal to P1 into A. So in the same way we will calculating the value of F2, that will be P2 into A. And the most important thing is the value of m we can calculate in the way that it will be density into the volume. So mass will be the density into volume, it will be rho into V, and in the way we can write that the rho into A into h. So h may be represented as the height, therefore students, with the help of this value we can put into our equation. Then we will get P2 into A is equal to P1 into A plus rho into A into G into bracket x1 minus x2. So A is on the either side of the equality sign, so it will be get cancelled. So remaining terms will be the P2 is equal to P1 plus rho into G into bracket x1 minus x2. So this is the equation that we have derived and which will be used to find the pressure inside the liquid. So this is the derivation that we have discussed in the previous lecture. So we have just took the small I over that. After that, students, this is the second case of the derivation, which is the pressure at the depth h below the surface of a liquid we have discussed. So for this derivation, for the expression of this equation, we have considered the x1 is equal to 0, as you can see in the diagram. So as it is lying, the top surface of that imaginary cylinder is lying exactly equal at the surface of that water. So x1 is equal to 0, and the p1 will be the p0, and the x2 is nothing but the height which is below the water surface, so it will be minus h, and the p2 is equal to p. Now by using this value, we can say the equation, we can derive the equation as p is equal to p0 plus rho into h into g. So this is the equation that gives us the total pressure and the absolute pressure P at depth h below the surface of the liquid. Now student, as we will see the next case also, that the P0, the pressure due to the atmosphere which acts on the surface of the liquid, and rho hg is the pressure due to the liquid at a depth. So these are the two things we also have to keep in mind. After the students, the last derivation that we were discussed in this case was the change of atmospheric pressure with the height. So this is the consideration, and it's a diagram you can see in your screen, on your screen. Now the imaginary cylinder is lying over the surface of the water, means the bottom surface of the imaginary cylinder will be lying over the surface of the water, and it is at the depth d. So you can see, to find the atmospheric pressure at a distance d above the liquid surface will be, you can see in the diagram. Now we will putting the value according to the arrangement of the diagram. So it will be the x1 will be the d, as it is the depth, and the p1 is equal to p, and the x2 is equal to 0, as it is lying over the surface of the water. Now the p2 will be 0, and the rho, that is the density of the liquid, will be equal to the density of that air. So by using this value, we can derive above equation as the P is equal to P0 minus D into rho, that the density of the air, into G, that is the gravity. So this is how we have discussed the three of the conditions of this change in atmospheric with the height, and rest of the two. So we'll see the next part of this chapter now. Now students, the next part of this chapter we will be discussing as the hydrostatic paradox. So in this point, you can see the diagram that we have to consider the interconnected vessels you can see in the figure. So when a liquid is poured in these different shaped vessels which are connected to each other. Now when a liquid is poured in any one section of the vessel, means suppose we just pour the water or the liquid in the section A, or you can pour the water in the section D or B or C, any one of the vessel you have to pour the water. Then what will happen? The level of liquid in all the vessels is the same, means the level of all the liquid, all the vessel liquid level will be the same. Now this observation is means you will be having the questions in your mind that why this happen. If you are pouring the water in any section, any vessel, then the water level will be same. So this is nothing but the concept of hydrostatic paradox. So students, before that we will see that one can feel that the pressure of the base of the vessel C would be more than at the base of the vessel B. So we can say that the liquid from vessel C would rise into the vessel B. However, it is never observed. Now you can see that the equation that above we have discussed tells that the pressure at the point depends only on the height of the liquid column above it. So it does not depend upon the shape of the vessel. So in this case, height of the liquid column is the same for all the vessels. Therefore, the pressure of the liquid column in each vessel is the same, and the system is in equilibrium. So we can say that this will sense that the liquid in vessel C does not rise into the vessel B. So this is the concept of hydrostatic paradox. Now you can see the diagram B, that is 2.10 diagram B. It shows the arrow indicate the force exerted against the liquid by the walls of the vessel. Means the walls of the vessels has been applying the pressure to the liquid to be in static position. Now, these forces are perpendicular to the walls of the vessel at each point. These forces can be resolved into vertical and the horizontal components. The vertical components act in upward direction. The weight of the liquid in section B is not balanced and the contribute the pressure at the base. So thus it will not be longer paradox as you will compare the diagram A with the B. So this will diagram A will be the in longer hydrostatic paradox than that of the diagram B you can see. Now students, the next part of this chapter we will see, which is Pascal's law. So the Pascal's law states that the pressure applied at any point of an enclosed fluid at rest is transmitted equally and undiminished to every point of fluid and also on walls of the container, provided by the effect of the gravity is neglected. Means this is the Pascal's law. Means if you think about the Pascal's law in simple way, then it will be liquid exerts equal pressure in all directions is the simple way to state the Pascal's law. But when this will be asked into the exam, then you have to explain all the terms which are given in this law. As Pascal's law states that the pressure applied at any point of an enclosed fluid, means the fluid should be enclosed by some isolated system and at rest is transmitted equally and undiminished to every point of fluid. Means you can say it will be enclosed by the system and transmitted equally. When we will apply the force in such a condition, then it will be transmitted equally in all the directions. So means it will be struck to the wall, it will be struck in all directions of that isolated walls, it will be struck equal in all direction. So this is the law that which we have to write when this law will be asked into the exam, or in simple way you can say that the liquid exert pressure equally in all the direction. This is the simplest form of the Pascal's law. Now in our daily life there are number of applications of the Pascal's law. In the hydraulic press, in the hydraulic brakes also there is the application of the Pascal's law, and in the different types of industries also which deals with the heavy loads or heavy duty operations, there is also the utilization of application of Pascal's law. Now out of that we will see few of the examples. Now students, this is the one of the examples that we are going to study, which is of the hydraulic lift. So hydraulic lift is the one of the example of the Pascal's law we will see in detail now. Now as we know that the hydraulic lift is used to lift a heavy object using a small force. The working of this machine will be seen which is based on the Pascal's law. Now as shown in figure, you can see that a tank containing a fluid is fitted with the two pistons. As you can see, the P1 two pistons as the S1 and S2, and S1 has the smaller area of cross section as you can see, while the A1 and A1 while S2 has the larger area of cross section as compared to the S1. Now as you can see, the condition is the A2, the area is too much greater than the A1. So if we apply the small force over the piston 1, then in the downward direction, then the piston S1 in downward direction will be moved and will generate the pressure is equal to F1 upon A1. Now students, hence therefore this pressure will be transmitted undiminished to the bigger piston S2. So a force of F2 which will be equal to P into A2 will be exerted in upward direction or upward to it. Now this F2 force will be F1 into A2 by A1. So A1 is nothing but the area of small piston and the A2 is nothing but the area of larger piston. So thus the F2 is the much larger than F1. A heavy load can be placed on S2. So can be lifted very easily and move down by applying a small force on S1. So this is the principle of hydraulic lift, which is totally based on the Pascal's law. So students, this much we have discussed about the mechanical properties of the fluid in this fifth video. So the next part of this chapter we will be discussing in the next video, that is in the video number 6. So if you have any problems or doubt, you can visit the previous video and can learn again. So we will meet in the next video. Thank you so much.